Today is the start of Unit 1.2, and we're beginning with slope or rate of change as our first topic. So the first thing I want to do before we get into it is talk about that vocabulary itself. So slope, you're probably familiar with, and we remember that one pretty well. But rate, or the entire phrase rate of change, is one that students tend to forget and not recognize when it comes up on a test or on STAR or something like that. So we want to remember that when we see the vocabulary rate or the full phrase rate of change, that we should immediately in our brain be translating that to slope. Or in terms of an equation, m, which we'll talk about in the next notes, I think. So when we see rate or rate of change, we need to just recognize that that is talking about the slope of a line. And the slope of a line deals with the idea of whether it is flat or steep. So steeper lines are bigger slope. So this steep line would be more sloped, and flatter would be less sloped. Kind of like when you're going up a hill. If you're riding your bike up a very kind of flattish hill, it's easier. So this is easy. And if you're riding your bike up a really steep hill, then that's going to be difficult. So, yeah. All right. So we have this warm-up where we have 4 different drivers, Jerry, Alicia, Calvin, and Marissa. And they're testing their car's gas mileage, filling the tanks to maximum, and then driving on a track at 65 miles per hour. So all of them are driving at the same speed, 65 miles per hour, until they run out of gas. The graph shows the amount of gas over time. So key thing with a graph is to know what we're looking at. So here we have our y-axis, the vertical one, is volume of gas. So that's how much gas is in the car. And the x-axis is time. So that's how long they've been driving. So this is the y-axis, which is vertical, and the x-axis, which is horizontal. Okay, so the warm-up is to write down statements in your notebook about it. If you didn't have a chance to do that in class, go ahead and do that in your copy of the notes. And then there's some questions here for us to go through, which I'm going to zoom out so we can see the graph and the questions. So question number 1 says, whose car has the largest tank? So the tank holds the gas, so the largest tank we could read as the most volume. So we look at our y-axis, and we look at where we started at time 0. So on our y-axis, Alicia looks like she holds the least gas. Calvin holds the second least. Marissa is in second most gas, and the most gas up here is Jerry. So we're looking at what we call the y-intercept of that graph, and we see that Jerry starts with the most gas, so he must have the largest tank. We know that because the story said filling the tanks to maximum. So I should be using a highlighter for that. So filling the tanks to maximum means that the amount they started with must be the amount their tank holds. So Jerry has the largest tank. Number 2 says who ran out of gas first. So our x-axis represents time, and it says who ran out first. So first would mean our earliest x-intercept. So Alicia ran out of gas at this time, Jerry ran out a little later, Calvin much later, and Marissa ran out the last. So who ran out of gas first would be Alicia. Who traveled the greatest distance? So that one's interesting because neither of our axes talks about distance. We have the x-axis, which is telling us about time, and the y-axis, which is telling us about the volume of gas. Neither of those things is a distance. So let's look at what other information we have. We underlined earlier, and now we can highlight, 65 miles per hour. So that means all of the cars are going the same speed. So if I travel 2 hours at 65 miles per hour, then I would travel a certain distance. I would multiply 2 hours times 65 miles per hour and go 130 miles. If I was driving 1 hour at 65 miles per hour, then I would multiply 1 times 65 and travel 65 miles. So because they're all traveling the same speed, they're all going 65 miles per hour, then we can directly relate the time they drove, the number of hours, so like number of hours, to the distance they traveled. Going twice as long is the same as going twice as far, but that's only because we know they're all going the same speed. So all going the same speed. And who traveled the greatest distance, which in our case is the same as the greatest time, we can see that Marissa traveled the greatest time. Number 4, who gets the worst gas mileage? So gas mileage has to do with how far your car can travel on 1 gallon of gas. So the other way of looking at that would be the worst gas mileage would be the most gas per hour. So whoever is using up gas the fastest has the worst gas mileage. So to find that out, we need to look at gas per hour. But before we do, I want to highlight this word. Let's use green. Green is important. So per. Per is a super important word when we're dealing with graphs of lines and slopes. Even when we're not dealing with linear graphs, per is very important because it tells us that we're looking at a slope or a rate of change. Even up here in our miles per hour, if we had a graph, so say we made a graph over here of 1 hour, 2 hours, and this was like 50 miles, 100 miles, 150 miles. So after 1 hour, we've gone 65 miles. After 2 hours, 135 miles. So that 65 miles per hour is giving us a slope, but it's for a graph that we're not actually dealing with. It's how far each of them travels relative to time. So that would be a different graph, and it would have hours down here and miles over here. So the main thing we want to know about that word per is per separates y and x. So notice in miles per hour, miles is on the y-axis, hours is on the x-axis. So any time that you're given blank per blank, you know that this one is the y variable and this one is the x variable just by the way that it's stated. So if I make $20 per day, then I know that dollars will be the y-axis and day will be the x-axis. All right, that was a really important little side trip because the word per is just so important. But let's go back to our question. Most gas per hour. So if we think about these as being like 1 unit per like major line here, so 1, 2, 3, 4, then we can see that Alicia traveled 1 time and 1 gas. So her rate would be 1 amount of gas over 1 amount of time. The second one, it looks like 1, 2, 3, is 1.5 time, but Jerry started with 1, 2, 3, 4 units of gas. So that would be 4 over 1.5 is how fast he's using up gas. Calvin has 3 units of time and 2 units of gas. And Marissa has 1, 2, 3, 4.5 units of time and 3 units of gas. So if we simplify all of those, then we'll see that this one is the biggest number, using the most gas per hour. So it's likely that Jerry has some sort of large, heavy truck that uses up gas more quickly than these other cars that are probably smaller and more gas efficient. So relative to the picture, what that means is this one is the steepest line. So the steepest uses the most gas per hour, or the most Y per X. So steepest equals more Y per X. All right, so Jerry has the worst gas mileage. Let's make some comparisons. How does Marissa's graph compare to Calvin's? So from what it looks like, the space in between them looks like it's staying the same all the way across. And that means these lines are a word we call parallel. You're probably familiar with parallel. So let's say, how do they compare? They look parallel. What can we determine about the gas mileage of their cars? So it's very similar or the same. We'll just say it's the same. So if they use gas at the same rate, then they would have the same gas mileage. Next, how does Marissa's graph compare to Jerry's? So Marissa's graph, we're going to say, is flatter because Jerry's is steeper. And what we can determine about gas mileage is better. So Marissa has better gas mileage than Jerry, which we've kind of identified because we already said Jerry has the worst, so everyone else is better. What does the intersection? So intersection means where two things meet. What does the intersection of Jerry's graph and Marissa's graph mean? So we have an intersection. Jerry is purple, Marissa is green. So our intersection is this point right here. That means that at that time, they had the same amount of gas remaining. It means their X and Y were equal. So same X and Y, that's what we see on the graph. But the meaning of that, remember, X is the amount of time and Y is the amount of gallons. So the meaning would be, at that time, they had the same gas remaining. So notice I took my observation from the graph, same X and Y, and I put that into more English-sounding words. So I took where I had X, and I said at that time, because time is X, and we took Y and said that's the amount of gas remaining, and then our comparison, they had the same amount. So turning an observation in a graph into English words is a useful thing to be able to describe the meaning of things. So when you see what does something mean, then it's asking you to explain it in like English words, not just in basic math or graph vocabulary. After some automotive work, Jerry is now getting better gas mileage. How would this affect his graph? So we kind of already talked about it would make the slope flatter. So worse gas mileage on our graph was steeper and better gas mileage was flatter. So it would flatten his line. So we could also say it would make the slope flatter. Another thing it would do, notice that we're looking on the x-axis. Everybody else, well, okay, let's think about what it would do to the graph if we flattened his line. So let's say we took his line starting from the same spot, but changed the angle so that I don't remember how I changed the angle on this ruler. It's different than the smart ruler. So let's say his line is, so it was really steep. Now it's going to be this angle because I don't know how to change the angle right now. And he's purple. So his new line would be something more like this. And that means we have two things. One, the line is flatter. And two, he drove for a longer time. So he can drive for a longer time, which we said in this case, because of the constant speed, is also a longer distance. So he can drive his truck longer before it runs out of gas. And then the last question on this warm-up is, suppose Calvin's car can hold 30 gallons of gas, and it took him 5 hours to run out of gas. What would be the function, rule, or equation that describes his car's gas usage? So we know that a line looks like y equals mx plus b. That's called slope-intercept form, and we'll have more notes on it very shortly, maybe like right after this. So we need to know what those things are. So remember, y is the amount of gas. X is the amount of time or hours. So it holds 30 gallons and took him 5 hours to run out of gas. So we would replace or substitute the amount of gas with 30, and we would set that equal to m times the amount of time he drove, which is 5, and I guess, actually, sorry, we can do this more simply. We're not quite ready for that yet. So this is the gas remaining, and this y-intercept would be the full tank of gas, which is what we're given here. So we don't actually need to calculate anything. We're given all the information that we need. So we would say y, the amount of gas remaining, is equal to the time that he drives. Okay, so we need to find the slope still. I feel like we need the next part of the notes for this, but we'll go ahead and calculate it. So we need the slope times x plus our y-intercept of 30. So to calculate the slope, we're actually going to scroll down just a little bit and look at what the rate of change or slope means, and then we will come back. So I'm going to highlight this missing piece of information here, which is the slope, and we'll come back to it in just a minute. So rate of change is a ratio, so that just means a fraction that describes on average how much one thing changes with respect to another. So in this case, rate of change, we often call on a graph rise over run, which, that's here, rise over run. We also can say that rise on a graph is the change in y. So I'm just going to highlight because it's already all written in. Change in y is the same as rise, and change in x is the same as run. So looking at a graph, when we're counting on a graph, so if we're looking at, let's say, this point right here on Jerry's graph, I would look at my rise and my run being, I went from up here where he started, my rise went down by that much. So I started here, I'm going from this point at the beginning, and my run went from here to here. So the amount of x change we call delta x, which is like a triangle, and the amount that y changed, need to switch colors and then switch back for some reason, change in y. So from this point to this point, I know that wasn't straight at all, my change in x and change in y are what we call rise and run. Great. So in other words, I'm not sure what goes there. That's all the ways of describing it. Rate of change, change in y, change in x, delta y, delta x. So this symbol right here is a Greek letter, kind of like how pi is a Greek letter. Delta is a Greek letter that we use to represent the idea of change. So you'll see that throughout math and science classes. And it means change in y and change in x. On a graph, that's rise over run. So in other words, I guess we're putting slope here. I'm not actually 100% sure what we're putting there, but I'm going to put slope. So slope is maybe m. I don't know. Maybe slope or m. So slope, which we call m, of a non-vertical line is the rise over the run. So change in y over change in x. The bigger, so this says the greater the absolute value of the slope, that means bigger, that will be a steeper line. The reason it says absolute value is that if I have a graph and I have a line that's going uphill at that slope, and I have another line that's going downhill, I don't care which way it's going. So think about riding your bike up a hill. Whether it's going up or down, a steeper hill is still steeper, right? It doesn't matter whether you're going uphill or downhill. Steepness doesn't care about direction. It's just how much closer to vertical a thing is. Slope can be greater absolute value of slope, steeper. So slope can be, as I just drew there, positive or negative, I think is what we're going for here. Or negative. So we have this guy called Mr. Slope Guy, who's a visual reminder that you can use to remember what positive or negative slopes are. So on his left side here, we have his left eye as a plus, and that line slants uphill. So this is a positive slope. It goes uphill as we go left to right. So uphill as we go that way. The right side of his eye is a negative symbol and a downhill sloped line. So this one is a negative slope, and it goes downhill as we go to the right. In the middle and the bottom are two that you probably have worked with just a little bit, which are two special kinds of lines. So let's use different colors. Let's use green. So if I have a completely flat line, then remember, closer to flat means less slope. So this is a line with no slope. So it doesn't go up or down at all. It's completely flat. So it has no slope. It's flat. It's horizontal. And it has a slope value of 0. So we go down to this mouth area where we have these two little kind of dimples or cheek marks that are zeros because this flat line, this horizontal line, has a slope of 0. Our last one is a special case where a line goes straight up and down. When a line goes straight up and down, we can't even talk about a slope because remember, slope is all about what happens as we go from left to right. But if I'm sitting on this line and I try to go to the right at all, the line is gone. It doesn't even exist anymore. So this is different than a flat line where there's no slope and it's flat. Here, the slope doesn't even exist. Like, we can't even talk about the concept of slope for a vertical line. So vertical lines are different than horizontal lines, but we easily get them confused because the normal things we think about slope for uphill and downhill don't apply to either of them, but in very different ways. So here, m is not 0. M is what we call undefined. So undefined is not the same as 0. It means that there isn't one, period. Whereas 0 means there is a slope and its value is 0. So that last part, I need to go to highlighter, is right here in the middle. So his nose forms a U shape standing for undefined. So that's the U here. And then we have a vertical line for the rest of his nose, or the bridge of his nose, I guess. So this is a visual you can sketch down on like a quiz paper or on scratch paper on a test if you need help remembering which of those things is which. Hopefully over time you'll internalize them and get used to them. But those are our 4 kinds of straight lines. We have uphill, positive, downhill, negative, horizontal, which is 0 slope, and vertical, which is undefined slope. So we can't even talk about what the slope is. All right, slope of any non-vertical line through any 2 points. So we call this thing here the slope formula. And it's a way of finding slope when we don't have a picture of a graph. So when we have a picture of a graph, we tend just to count the rise and the run. So like here, I would say wow, I put rise and run backwards. I hope somebody noticed that and that you were upset about it. Let's fix that. I don't know how I managed to do that, but we all make mistakes. So change in X is the run, and change in Y is the rise, of course. Wow, what a mistake. So on a graph, we typically just count. So here, if I'm looking at my run, it would be 1, 2 is the run, and the rise would be 1, 2, so my rise is also 2. But my rise is negative because it's decreasing. So that's what we do on a graph. But if we don't have a graph, we're able to just use coordinates of 2 points and calculate the slope by finding the rise and run that way. So the slope formula, which is on your star chart, says m equals y2 minus y1 divided by x2 minus x1. So what does that mean? If I have a graph and there's a point here, say that point is at 1, 4, and then there's a point over here, 1, 2, let's say that's at 5, 6. That looks about reasonable. Then if I want to find the slope between those two without a graph, all I have is the numbers, then I can calculate the rise and run the same way I would count it on a graph. So my rise is how far I went up. So this direction, I went from 4 to 6. So I subtract 6 minus 4, which I guess I should label these. This is x1, y1, and x2, y2. What does that mean? Well, we know that we write ordered pairs as x, y. We put the left to right number first and the up and down number second. The subscripts, which is what we call these little 1s and 2s, mean that this is point number 1, and this one is point number 2. And it doesn't matter which is which. If I reverse that and call the one on the left point 2 and the one on the right point 1, I'll get the exact same slope. It doesn't matter which we call which. So these little subscripts are like labels. So it's saying I need a highlighter. Which x are we talking about with x1? We're talking about the x value of the one we're calling point number 1. So that x value is going to be 1. Whereas the x value of point 2 is going to be over here in the first position on point 2. All right, so our rise is 6 minus 4, and our run would be 5 minus 1. So again, it doesn't matter which one is point 1 and point 2, but it does matter that they go in the same order. So here, I put the 6 and 5 first, but they're aligned this way because they're the same point. So this is point number 2, and these two, the 4 and the 1, are point number 1. If I reversed it and did 4 minus 6 over 1 minus 5, I would get the same exact answer, which is 2 over 4, or 1/2. So that's how I can find slope by plugging in 2 ordered pairs, rather than actually having a graph or sketching a graph like I did here. So I went up 2 units and right 4 units from 1 to 5. So that's how I got my slope of 2 over 4, which simplifies to 1/2. So that's the note part about Mr. Slope Guy and about the slope formula. Now we're going to look at some practice problems and what things might look like that you see on this topic. So my rate of change for this table. The thing we need to remember about a table is that it's just a list of ordered pairs. So these x's and y's are the same thing we see in a table. So I have this x and y, and I have this x and y, and this x and y, and this x and y. In this case, it hasn't told us that this is a straight line, so we really should figure out that it is a straight line first, but I know that it is, so I'm going to skip that step. They haven't given us the option of this being not a straight line. So that means we just need any two of our points. So this is point number 1, 2, 3, 4. Any two of them will let us plug in these numbers to the slope formula. So we would do, say, pick point number 1 and 2, these two right here. If I do my y2, that's 6. Nope, that's x2. If I do y2, that would be 84. Remember that in a table, x is on top, y is on bottom. So I have 84 minus 42 divided by 42 divided by 6 minus 3. Then I need to simplify that. So my like terms on top, I combine them to get 42, and on bottom I get 3, and then I can simplify that to just 14. So my slope here, my rate of change, is going to be 14. Remember that that's 14 over 1. So if I wanted to think of if m is 14, then that means if I were graphing it, my rise would be 14, and my run would be 1. Because 14 is the same as 14 over 1. There's always a hidden denominator of 1 under every whole number. So now I want to go back. So that's how we would use the slope formula. If it were me, I would advise not using the slope formula for a table. Instead, what I would do is use rise and run counting the way we would on a graph. So I look from 3 to 6, I have a run of 3 because I'm adding 3. And from 42 to 84, I have a rise of 42 because I'm adding 42. So then I would just say my slope is my rise over my run, which is 42 over 3. And notice that's the exact same answer we got with the slope formula, but I didn't have to actually plug in all of these numbers. So typically from a table, rather than using the actual slope formula, we just count rise and run, similar to how we would on a graph. All right, so there's 2 more tables and a graph here. So let's do one of the tables and the graph. So my rate of change, my run is 4, my rise is 8. 4. Oh, I should have zoomed back in since we got out of the warm-up part. So I have 4 and 8. So my rise over run, I have 8 over 4, which simplifies to just 2. I could put 2 over 1, but we don't write a 1 underneath whole numbers. On my graph, I'm going to do a similar thing of counting, like jump counting, like what I did with these arrows. I have to be really careful on a graph, though, to look at what it's counting by. So this graph is not counting by ones, so a really common mistake, and something that STAR in particular loves to test, is looking if you're just counting the lines. So here, for my run from here to here, 1, 2, 3, 4 lines, and here, my rise is 1, 2, 3 lines. So on STAR, a lot of times they expect you to put a slope of 3 over 4, but that's not correct. So make sure that before you label this as 4 and 3, you check what those numbers actually represent. So I went from 4 up to 12. So this is not a 4, this is an 8 that I went here. From 4 to 12, I went 8 units. Similarly, on the vertical axis, I went from in between here, which is 30, up to 60. So that was a rise of 30. So instead of 3 over 4, I actually have 30 over 8, which I can simplify by dividing by 2 and put 15 over 4. So my slope here would be 15/4. I would prefer we generally leave slopes as fractions because then we can see a rise and a run. Technically, you could also say that this slope is 3.75. The problem is if you're graphing that or trying to interpret a rise and run from that, it's a lot more ugly than if we just leave it as 15 over 4. All right, finding slope from slope formula. So we have 2 points, and I'm actually going to talk about an alternative here. So I don't generally like the slope formula or formulas in general. It is on your star chart, which is pretty handy. But we have m equals y2 minus y1 over x2 minus x1. So then we would plug in with 2, -3, and -4, 5. It's really helpful, especially when you're new at this, to label this. Let me make this smaller. So if we call this x1, y1 and x2, y2, it'll make sure that we put things in the correct spot. So now I can see that y2 is 5 minus y1 is -3. So I need to make sure that I'm careful with my signs. The slope formula is really easy to get signs mixed up. So we have minus -3. And then on bottom we have x2, which is -4, minus x1, which is 2. So that is going to be equal to 5 plus 3. Anytime we have minus a negative, we make it a plus. So 5 plus 3 is 8. -4 minus 2 is -6. So I have a negative and another negative. I get a bigger negative number. And that simplifies to 4 over -3. By convention or math rules, we never leave a negative in the denominator. So rather than writing it as 4 over -3, we always write it as -4/3. So think of it as we have 4/3, and that whole thing is negative, but we always show the sign on the top number. So we put -4 on top and 3 on bottom. So I promised you I was going to show you an alternative here. So what I typically do rather than using the slope formula is treat it as if these two values or two ordered pairs were in a table. So I say this is my change in x, and this is my change in y. So just like we did with the tables up above, I'm going to go from -3 to 5, I'm adding 8. So this was my run, and this was my rise. So then I just go straight to putting 8 over -6, and then simplify that to -4/3. So you can use the kind of like skip counting or arrow thing like we did up here on the tables and the graph with ordered pairs as well. Just you're basically acting like they're two items in a table. Then they have a graph here. I can't draw graphs on this tablet, so we don't have a y-intercept. Oh, we have the 2 points. Okay, I guess we should practice graphing points. We haven't done that yet this year. So 2, -3. Remember that the x comes first. So this is the x-axis and y-axis. So we're going 2 units to the right, and -3 means 3 units down. So I'm going to put a dot right here at 2, -3. And then we have -4, 5. Negative x is left, so 1, 2, 3, 4 left, and 5 up. So that's way up here at the top. And then we would use a ruler, which again, I don't remember how to tilt this ruler. And I don't have a touch screen. Maybe with the mouse. Oh, I can use the mouse wheel well, maybe. I can use the mouse wheel to tilt my ruler. Neat. Okay, so then we would line up our ruler, or you may use your ID badge holder that helps you make straight lines. And we connect those with a straight line. Then we can hide the ruler. And then we put arrows at the end of a line to show that it goes on forever. So we'll talk more about drawing lines in the coming lessons, but lines should always go all the way across the graph. They should be straight, drawn with a ruler, and they should have arrows at both ends. All right, there's a few more examples for finding the slope. I'm going to let you try these ones because this video is already pretty long. I'm just going to show you 2 of these. So this one here, I notice that when I look at my change in x, it's 0. So think about plugging that into rise over run. I'm going to have something over 0. Anytime we have something over 0, then we end up with an undefined slope. And if we think about what that looks like on a graph, I have 8, -1, and 8, -4. So those are right above each other, meaning I'm going to end up with a vertical line. So my slope here, I'm going to put undefined rather than putting a number. Contrast that with this one, where my y value didn't change. Y value I usually draw underneath. So if my y value doesn't change, then my rise is 0. So if my rise is 0, I have 0 on top over something on the bottom. So we should know that 0 divided by anything is 0. So here my slope equals 0. It's a horizontal line. And if you think about sketching it, 5, -2 would be here, and 10, -2 would be here. So I'm getting a horizontal line, meaning I have a slope of 0. So those are the ones that are going to trip you up the most, where they're flat lines or vertical lines. Same thing with a graph. We have this second graph here has a horizontal line, so the slope is 0. I don't need a slope formula. I can just go straight to saying the slope is 0. All right, last part of notes for today is finding a missing value. So here I have a point, and then I have half of a point, but I'm missing the other piece of it. So I know the slope. So in this case, m is equal to -3. I know x1, and I know x2 and y2, but the thing that I'm missing is y1. So I'm going to plug these into my slope formula and solve for the missing thing. So the way we'll do that, our slope formula says y2 minus y1 over x2 minus x1. Let's rewrite. So we know all but one of these things, and that means we can solve it. So m is -3. y2 is -1. Minus y1, I don't know, so I'm going to leave that as my variable. And then on bottom, x2 is 6, minus x1 is 2. So now we're going to use our equation solving skills to figure out what y1 is. Remember, we need to simplify like terms first. So my first step is going to be -3 equals -1 minus y1 divided by 4. My next step, I need to get rid of this denominator. So I'm going to multiply both sides by 4. I get 12 is equal to -1 minus y1. 1. Next, I need to add 1 to both sides. That gives me 13 equals -y1. And then finally, my y1 needs to be positive. So I'm going to multiply both sides by -1 and get rid of that negative sign. So I'll have -13 equals y1, and that's my solution. So I go through my normal equation solving steps to find that missing thing, making sure I do my order of operations in reverse. So I collected like terms, and then I did multiplication, addition, and then division or multiplication. All right, so our slope here, or our missing value is y1 equals -13. There's some more missing coordinate problems. They work exactly the same as what I just did, so I'll leave those for you to be able to practice. And that's it for these notes.